Hi everyone, I'm Deepak Pathak. I'm currently a researcher at Facebook AI Research, and I'll be starting as assistant professor at Carnegie Mellon University in this fall 2020. Today, I'll talk about how can we design pre-training strategies for robotic agents, and what are the challenges in doing so. Okay, let me begin. So, deep learning has been successful in number of fields for the last several years across a number of challenging tasks. However, the key success of deep learning does not lie in training a giant model on a collection of large data set, but in the fact that once we have trained the network, these pre-trained representations transfer really well to a wide variety of tasks. For instance, in computer vision, I can take these embeddings and transfer them to detection, segmentation, boundary, video, and whatnot. In fact, this kind of success of transferring pre-trained representations is not limited to computer vision. This has been the case in language, speech, in fact, in any domain where one could collect large amount of passive data. A usual strategy today for solving a new downstream task is roughly to go and download a giant model which was trained on large data set like ResNet on ImageNet for vision, BERT for language, and then for your own downstream task, collect some new labeled examples and then fine tune on those examples. And more often than not, this will result into the victory and your model will perform really well and you can move on to the next challenge. Now, can we transfer the same kind of success we have seen in building pre-trained representations for all these tasks to robotics? So robotics is similar and different to other passive domains like vision, language. In It's similar in certain aspects, such as the problem is also open world, and the input is unstructured in the sense that robot can receive an image from a camera or haptic sensing from a touch sensor. But it's different in the sense that the agent is embodied in case of robotics. So data is not IID, and it depends on the agent's current action. The agent's current action defines what data it will receive next. Moreover, it's very hard to define data sets in case of robotic tasks. It's very expensive and time consuming. To address some of these challenges, there have been several formalisms which are proposed in the literature. Roughly, they can be categorized into learning from demonstrations to handle non-ID data, or reinforcement learning, learning from rewards, or model-based control where you learn a model from agent's experience. However, despite these formalisms and these differences and similarities, I would argue there are two key challenges which makes it very hard to even think of a setup where one could pre-train a general purpose controller for an arbitrary new robot. And those two challenges are as follows. First, it's quite unclear in the case of embodied agent, which can perform a bunch of tasks, what task should I pre-train on? For instance, in case of vision, we have seen that we can train on classification or detection, and these models transfer really well to several other tasks. For language, we have seen that a model that predicts word to vec or like interpolation or extrapolation works in practice really well for the task as well. But in fact, in the case of embodied agent, an agent can perform several tasks in a daily routine. For instance, over here, like picking something, grasping, reaching, and whatnot. How do I define the task that I should pre-train on? If I go and pre-train on all of these tasks, it would be really expensive and not scalable. Correct? Furthermore, to add to the challenge, even if we could pick a task, we have seen this over and over in robotics that it's really hard to generalize from one task to other. For instance, Boston Dynamics robot, which can do parallel trick over here, fails catastrophically when asked to perform a really simple task of putting a block on a shelf. So, okay, as we see, okay, it just falls completely on itself. And the second challenge is that if I create a new robot, or if someone else creates a new robot, it's not even understandable what does a pre-trained controller or pre-trained policy for that robot mean, even if it's for the same task. For instance, because that's the case because every robot is different. Every robot has a different shape, different morphology. For instance, in this NASA dexterous manipulator looks so different from all of these other agents. Now, what does it even mean to download a policy which was trained on some other robot somewhere else for this robot? Ideally, we would like to share the experience of different kind of robots together, but this adds to the problem of even approaching this question in the first place. So in this talk today, I'll talk about some of our early effort towards addressing this gap between passive pre-trained general systems in vision or language and in robotics, and see how can we even approach this problem, which seems uh, hard to conceive or to get our head around. And these works are still in the early direction, and I will show results in simulation, games, and real robots. But there is still a long way to go in bridging this gap. So let me begin the talk. In the first part of the talk, I'll focus on the question of how can we pre-train agents such that it can generalize to new tasks, and possibly try to answer the question of which task to pick at training time. And second part of the talk, I'll talk about how can we build these controllers such that they can generalize to a new robot shape, which they have never seen before. Okay, so let's begin and look at the first problem over here. Before we go into one of the proposed, before we go into our proposal, let's look at an example task and see how can we address in the current with the current domain approaches. So let's take a task over here where a robot sees an image of a rope in front of it, and its goal is to tie the knot in that image. So it wants to find a series of actions that accomplish this task. One common way to approach this problem in robotics is imitation learning, where an expert manually controls the robot to collect demonstrations of state action pairs, and then these are used to train the policy. Now, this is very tedious for the expert, and the same process has to be repeated over and over for every new task. Some approaches can learn from few demonstrations at testing, but still use large amount of supervision at training time. The other family of approaches that tackle this problem is comes under reinforcement learning, where the idea is as follows: that you start with a current image and you train a robot policy which outputs a series of action that leads to next state, such that over time the robot reaches a goal. And when the robot reaches the goal image, it receives a reward function like a candy. If it ties this knot, it gets a +1, and the goal of the policy is to train itself such that the overall reward is maximized over time. But in the beginning of the training, the policy starts by being random. So if a robot is acting randomly, how likely is it the case that it will hit on this task of tying the knot? Well, it's extremely unlikely. So it will take a huge time for the robot to even get the first bit of reward, approximately these many interactions by some calculation in the setup. So how do we even tackle this problem? Right? So that's why reinforcement learning in practice is not as glorious. In fact, as you see over here, this agent can play the game of Atari by only looking at the screen. But in practice, these agents look at the score of the game as a supervision signal, which provides a dense reward at almost every time step. In fact, even the task of navigation, where the goal is usually a sparse target location to reach to, most approaches shape the reward function by adding these apples in between. But real world does not give you apples. In real world, the reward could be delayed by days, months, of year, such that it's hard to propagate back to where you are. So how does this child over here know what actions to take so as to become pilot 20 years later? Does she optimize the reward and backprop the signals out of the brain? Perhaps not, right? In fact, psychologists argue that human babies are not even driven by the end goal. They are driven by something known as intrinsic motivation or curiosity, where they go and explore and do things that they like a kid over here happily playing with Legos, not trying to get into MIT for his PhD or something like that, right? Trying to enjoy and learn skills which can later be used to achieve different tasks. can we use these skills to pre-train our agent without can we use this idea of curiosity or interesting motivation to pre-train the agent to learn skills which can then later be used for future tasks? So at pre-training time, what if we remove the notion of task itself? But the question is, how do we formulate this notion of curiosity? And this is a question which I've been investigating for several years at this point, and we began like several years ago. So I'll try to give a brief review of where we have reached in the last several years and where we are going in the direction. But before I do that, let me give you a rough intuition about the idea of curiosity-driven learning. And the idea is as follows. Suppose we have an agent, and the agent sees an image of the environment, and it has some action. Now, there is no other information, no reward, no goal. Now, our idea is to pre-train the agent by its own intrinsic experience and its own intrinsic curiosity. So what it does, it tries to act randomly in the environment. It presses left, it goes left, presses right, it goes right, presses up, goes up, presses down, it comes down. So in this Super Mario world, it tries to collect experience by acting in this world. Now, the key quality of the agent is that it tries to build a model of the world by using this data. And the model is a forward model which tries to predict the consequence of each action. So given an action, let's say for move forward, like press upward, the agent tries to predict what will happen if I press this. It expects to go up and come down because that's what happened earlier, correct? In reality, if the same thing happens, well, it becomes happy and its belief get reinforced. Let's see one more example. Let's say there's a pillar over here and it expects the same action to go up and come down, but because of pillar, it goes up but it does not come down. Now, what we do is that we use this failure in prediction as a signal to define curiosity of the agent. We say the agent is curious if it fails to predict the consequence of its own actions. And when it's curious, it should explore this environment even further. So the high level idea is as follows: build a model, use the model to make predictions. If predictions are bad, the agent gets curious, it goes back and explores whatever it is curious about. As it explores it more, it builds a model. Model improves. And as the model improves, its prediction error goes down, its curiosity becomes low. Now the policy has to figure out something else which makes it curious. So as a matter of fact, if you think about this, this creates a chain reaction of events where the agent learns continually on its own and it keeps improving its pre-trained model completely on its own without having the knowledge of task. Let us see how does this work in this simple environment. In fact, there are several approaches which people have proposed before this for exploration. But most of the prior work was in the context of achieving some end goal. While our idea over here is to pre-train the controller without any end goal. And end goal will be given at test time later. So it's a pre-training phase. Okay. Let's see some result. So in this case, we remove the tag, reward, and we let the agent be curious in this environment to pre-train itself. And in the beginning of training, well, it just jumps around, goes here and there, does nothing. It builds a model or something, right? Now, after training for some time, this agent, using curiosity-driven learning, this kind of behavior emerges where it just learns to make progress through the game. And why does it the case? Because it doesn't want to stay at one location. It gets bored very quickly. So it wants to move forward and explore. Well, then why does it kill the enemies? Well, if it doesn't kill the enemies might kill the agent, in which case it will die. And when it dies, it cannot be curious. So to stay alive, to be curious, it learns to kill the enemies. So this whole chain reaction of things just emerges by the simple idea of trying to do something new, which the agent has not done before. Okay. Now, this simple idea or a three-line algorithm is very general, and we have tried to apply this over the years on several environments, like not just that game, but all of these Atari games, like almost any benchmark where people have tried reinforcement learning on. We have tried this curiosity-driven learning with the caveat that we don't use any reward function, so it's completely unsupervised. Like in this two-player game, both of them are curious. Without telling any instructions, they learn to play the game because they don't want to lose the game. Whoever loses gets bored, correct? Using curiosity, this robotic ant learns to locomote and learns this walking-like behavior. We can also put curiosity on an embodied agent for navigation, and it learns the skills of navigation of going around without ever being told or supervised for any of these things. It's completely emergent. And these skills also transfer from one map to other map, even though agent doesn't know about the map or textures. What about real robots? Well, before I show you a real robot, let me show you what the most common approach that people perform for exploration in robot learning, which is random exploration. Now, as you see over here, if I try random exploration on this setup, it doesn't even touch the object. So if this is the dominant approach today, why is it the case that these other papers show that robots can do really well? Well, the catch is in most of those papers, you would see that there are lots of objects at a small location, and they have hundreds of these robots. Now, we made the task harder by only giving sparse set of objects so that randomly it cannot go and touch any object. It has to do something smart to do that. Furthermore, we are in academia, so not I would say rather poor, so we cannot really afford hundreds of objects than being at a company like Google or something else. And but what we do, we let the agent be curious. And in few hours of curiosity-driven training, our robot gets interested in doing interesting things with the objects, in moving them, and in collecting interesting data, which can then later use to. It learns these skills, which can then later use to plan for new tasks. Okay, so far we talked about how do we pre-train the agent without having any knowledge of task. But our eventual goal is to go from exploration, like pre-training phase, to achieving task, correct? Now, how do we do that? Well, we argue the most efficient way to go from exploration to achieving task is by planning. What do I mean by that? Is that given a goal or a task at test time, the agent can use its exploration models to plan in imagination as to how should it roll it out such that it can achieve that task. At a very high level, the pipeline that we follow is that at training time, agent explores the environment and distills the exploration into models. And models are used to explore the environment. This is what happens at training time. Then at test time, once the models are trained, given a new goal at test time, the agent goes and plans for this new goal. So you can either fine tune the model at test time, or you cannot even fine tune. Without any new sample or zero shot, you can plan for new scenarios. So since we are using planning over here, our agent is usually able to adapt to new tasks, which it has not been told about at training time without any further fine tuning. For instance, a cheetah robot over here can do forward running, backward flip, forward flip in this task. Now, one of the directions we have been exploring recently is that since we are trying to plan at test time for new goal, can we also use planning for exploration? And in fact, this is the recent work which is going to appear in ICML, where we incorporate explicit planning in the exploration phase itself. So like the idea I mentioned earlier, where the agent builds a model and tries to predict what will happen next, via planning at exploration time, we don't just predict what will happen next. Our agent actually plans completely in imagination what will happen next, and then next, and then next, and then next. And then in imagination, it tries to compute how much curious it will be if it takes this series of action, rather than only reasoning about the first action or the first couple of actions. And in this work, we propose a new formulation of curiosity where we use disagreement instead of prediction error, which allows us to train a differentiable and backpropagable system in a very efficient manner. For more details, please check out the paper. This was led by Ramanan and Oleg from UPenn. Okay, so what did we find in this paper? So what we found in this paper is that by incorporating planning during exploration time, the exploration itself becomes really efficient, such that our agents able to match the performance of an oracle Oracle agent which had access to rewards at training time. So, for instance, over here, without using any new samples for training or any supervision at training or test time, our agents perform similar to the Oracle. So the curves to look, so y-axis is the performance and x is the number of training samples, and orange is the Oracle and green is our method. So in most of the cases, green agent eventually ends up catching up with the Oracle, even though it does not see any supervised sample at training time. In some cases, there is still some gap. So in those cases, we just add 10 to 15 supervised episodes. And as soon as we add the supervised episode, the performance of our agent, which is learning in a completely self-supervised exploration phase, just jumps immediately to match the Oracle model, which has access to rewards at training time. So, what we are able to show in this work is that by incorporating planning into the training time as well, we are able to efficiently explore such that we can adapt to new tasks at test time. So these previous results were in simulation and mostly in the DM control environment. But what about real robots? So in fact, we have also followed similar line of regime in a different work in the real robotic scenarios as well, where we go from exploration to build model building and then to achieving task. And so let me show you some examples over here. In fact, let me show you the example of not time, where the agent, instead of training via reinforcement learning or imitation learning for the not time task, we let the agent explore. This exploration is used to build models. And then at test time, same robot is asked to solve any of those tasks. Like it is asked, can you make this L shape, S shape, or tie a knot? And at test time, a human comes and shows the robot how to tie a knot by only showing a sparse sequence of images. And then the robot can tie the knot from its own perspective without ever being trained for it. This is just a test time rollout. It's not training for this task. Similarly, for navigation as well, you can leave the agent in an environment, let it explore and build models, and take the same robot, put in a new environment, give it a goal image to go to. It's a new environment, so no map, and the agent can try to maneuver to reach the goal image. So note that you can do this kind of task with SIFT or SLAM kind of approaches. But the cool part here is that this is an emergent behavior and the robot was never trained for this. So the pre-training policy was not even aware of this task. So far, I have given you some examples and evidence of how can curiosity-driven learning serve as a potential solution for designing pre-trained policies for agents which are agnostic to the knowledge of downstream tasks. But what if my robot is different from your robot? Right? Well, everyone's robot is usually different. So how do I go from one robot to new robot? What kind of approach do we use over there? So let's look at deep reinforcement learning and let's see how much promise does it hold for this kind of task. Well, it has been very successful across different labs in the world in solving particular tasks on their robot separately. But how well does it generalize? Well, in fact, what we have found that reinforcement learning approaches are really hard to generalize. And this is a known fact. There are papers on how hard it is to train RL for robot control, even on one agent at training time. Like it needs a lot of tuning, lot of things have to get right. And even if you could train it well, it's really hard to generalize. If I change one limb, one motor in this agent, it just completely fails at test time. Okay. Some prior work have tried to address this problem by training RL agent or robotic agents on a collection of robots. For instance, on the left, it looks the same, but they have different number of units in the arm. And on the right, it's like a caterpillar with they train on 2 leg, 4 leg, 6 leg. So what you can notice over here that these approaches are very limiting in the sense that they assume that the topology of the robot is the same, because it's very hard to imagine how do you even generalize to a robot with a different topology, right? So the question of generalizing across robots or building a general purpose controller is actually a very hard one, and something which has not been yet addressed in the literature. But maybe there is no clear way around this problem. If we really want to tackle the problem of learning pre-trained policies for robots, which can generalize to new robots, we have to bite the bullet and we have to train the policy on a variety of robots. Because perhaps then these controllers can generalize to new ones and give some decent behavior, like we see by pre-trained models in other areas of deep learning. So our goal in this part of the talk is to see how can we pre-train a single policy for all of these diverse robots. So they're like Walker, Hopper, these 2D humanoids, and Cheetah, like 30 plus agents, etc., etc. And our hope is if we can do that, then hopefully the policy will generalize to new shapes as well without even fine tuning. So like a pre-trained downloaded model. But it's quite challenging. Like if you even think about this problem, it's unclear how to even approach this kind of setup because each robot has a different action space, different input space, correct? And in fact, the same policy cannot even function across all of them because different gates are needed. So like a humanoid can walk or run, but what you see, let me try to point. So what you see, like these humanoids can walk while these hoppers can hop. So they have to have a different gait, right? So how do I even approach this problem? So before we even go there, like before our approach, first question is why is it even possible? Like, do we have any evidence of such kind of thing in nature? So in fact, when we were trying to see the possible connections in biology, we found this long line of work in biomechanics where people have shown that in nature, even though if different like six-legged like cockroach, crab, humans, dog, 6 to 8 four-legged, all these different animals which are apparently different morphology, they apply similar kind of force on the ground. Their patterns are similar, which is a suggestion that maybe there are some shared locomotion patterns across species and animals in nature. And in fact, there is something called there are species of animals called precocial animals, which have something which is close to this pre-training kind of setup. Because when like horses, babies, or giraffe babies, as soon as they are born, they are able to walk or stand within hours after birth. And for instance, in few days they start to run and do interesting things. So they potentially they are not spending at any time at all in learning these controllers after their birth. So they have this notion of pre-trained downloaded controller uh, in the body, and it may be about muscle strength or the way my body is designed, but this is going through this genetic bottleneck where they are able to just immediately get to this stage. So somewhat our goal in this project is to go this kind of direction where learn a policy such that which can basically transfer zero shot to any arbitrary shape after having trained on a variety of shape at training time. But how do you even approach this problem? So before I go into the detail, let me show you a teaser result that we are indeed able to learn a single policy to control many of these agents. So it's a single controller that works across all of them and gives reasonable result. And then towards the end of this part, I'll show how well these generalize to potentially never unseen new robots. Okay. So how is this policy learned? So let's go in reverse. Let's try to find the approach over here. Well, the key idea of our approach here is that since every agent has a different different number of motors and limbs, it does not quite make sense to train a policy for the whole agent. We should probably train policies for each motor or limb of the agent and then share that policy across all limbs of all the agents. Okay. So I said quite a few words. Let me just try to explain that. So suppose this is my robot. Now I will train a policy for each motor or limb, like a hand or and then share that policy for across all the limbs. If I have tens of these robots, I'll share the same policy across their limbs as well. So the policy is shared across motors of the same robot across robot. So now this seems like this basically reminds us of the nature of compositionality, but which has been very powerful and successful in language and other domains as well. But the compositionality in this domain is not just at the level of software; it's at the level of software as well as hardware. And our hypothesis, or what we show in the project, is that having this compositional structure not only helps you generalize to new agent, it actually helps you learn policies which completely outperform current methods that learn a shared policy, that learn a single policy for the whole agent, and which is quite surprising and interesting. So unlike language, where you can are given the parser from off-the-shelf parser to parse the sentence into some modular structure, these agents have to discover their own compositional structure over time. So the question is, how do you learn these compositional controllers? Well, in this line of work, we build upon our previous NeurIPS paper from last NeurIPS, where we tried to design control algorithms for self-assembling agents, which kind of combine from different motors into a single agent. And the key idea over there is that you learn a same policy for every motor of the agent. So let me go in a bit more detail as to how do we leverage this key idea to build a controller for the whole suite of agents. Okay, so now let's try to understand it with this conceptual figure over here. Let's say you have two agents, one on the left and one on the right, with three limbs and three limbs in the star shape, and you are sharing the policy between, let's say, this limb, this motor, and this motor over here. Now, what you can notice, so the same policy is used at all the motors. So all the blue location, same policy is used. Not only this agent and the right agent as well. Now, if you see, the same policy is used here as well as here as well as here, right? So same policy is used on top of the point. So you have a policy network. There is a policy network on top of it as well as bottom of it, right? So, and you want the flexibility to arrange them in arbitrary ways, correct? Now this reminds you of something, and that something is like Lego blocks. Basically, you want to treat your policy network as Lego blocks. I should be able to reconfigure my Lego blocks in the hardware in arbitrary ways, and corresponding to that, I should be able to reconfigure my policy network in the same manner as Lego blocks. But the problem is policies are not Lego blocks, because in a Lego block, the input of one can be the output of other. But in a policy, the output and input can live in different space, correct? So how do we go about this problem? So what we do is we add an extra input to the policy. Let's call it message input X. And the policy modifies this and generates another output called X prime. And we make sure that these live in the same dimension. Okay, like 64 dimensional vectors, and they are learned vectors. Now, these message vectors kind of act as hook of Lego blocks for our case. So for instance, given this agent over here, I have this shared policy, right? What I'll do is, if I have to apply this policy on this robot, I'll copy it 3 times because it has 3 motors. Okay, 3 times copy. Now, how do I attach them together? So I'll take the message output of bottom policy and pass it to the top, and then pass the top of middle policy to the bottom of the other policy. I can just connect these 3 policies via these message vectors because they live in the same dimension. And now this shared graph network is my policy for this new agent. So this is different from graph network in the sense that I'm using the same policy everywhere, and they are just communicating via messages. There is no other aggregation function on top of these modules. Okay. But how does it help you adapt across robots? Well, it's again very simple. If I have a robot of this shape, I have a corresponding policy like this. If I have another robot which has this limb moved from here to here, like let's say this other robot. Now what will I do? I will just cut a policy from here and paste it at that location because it's the same policy. I can arrange them in arbitrary fashion. So at test time, if my robot has a different shape, or even more number of limbs, I can always adapt by changing the structure. So this kind of approach gets around fine tuning because it is adapting by conditioning on a new policy. Okay, so we call them shared modular policies, and we share them across all the agents, across the limbs of all the agents. Now the question is, how do we pass these messages? Because now these policies can talk in multiple manner. In the interest of time, I'll only talk about one scheme, which is really simple. Since all these morphologies have a tree structure, you can find a topological ordering of the graph. You can pick any arbitrary root node and all the other and the leaf nodes. Then you pass from leaf nodes to root node like this, and then root node back to leaf node. So like two-way message passing. So like this is similar to belief propagation in Bayesian trees from statistical learning. Okay, now let's look at some results. So as we see over here, earlier I showed that it's very hard to train an RL policy for more than one agent. But over here, we show that we train a single policy for all of these agents. And as you can see, even the policies shared across everyone, it shows very different behaviors depending on the shape. Like this one is trying to walk, this one is trying to hop, this is trying to hop. Furthermore, over here, if you see, this agent is trying to crawl because it only has one leg. This one is showing alternate walking behavior. There are more variants in this example where if you look at this agent, this follows a very different gait because the back leg is very short compared to this agent, which follows. And the surprising part is all these different gaits are being shown, but the policy is the same. The policy is the same across all of these agents, but the behaviors are so much diverse, and the same policy behaves differently depending on the shape of the robot, which is very nice. Now, again, the most promise, the part that we promised. Now, the reason we are doing all this is to generalize to new unseen agents. Now, I showed three categories. In this case, these are held out agents, but from similar distribution. And of course, they work reasonably well, and they can generalize and show different behaviors. This one walks, this one hops, right? But I can also now try very different shapes. Like these shapes are very different from what's seen at training time. Like they have monstrous looking agent. Some of them have really heavy hands. Some of them has really long neck. This is something weird, and this is too many limbs. So they more or less do reasonable. And note that this is completely zero shot. This is like downloading a model and running on the robot. It's not even training on this robot, even for one sample. So the performance improves very quickly if you train on these robots. But we are showing zero shot results over here. You can also add objects at test time directly, even though the notion of idea of objects was not even there in the training time. And these policies can still adapt to these very different scenarios, and which kind of displays the power of modularity in these scenarios. There are some failure examples as well. Like if I add too much weight to the humanoid, like in between or on the left in the hopper, or what if I even remove the legs of the humanoid on the right? How will it even walk? And it shows the muscle power here is not enough for it to move, but it shows decent trajectories. But these are the failure examples for our approach over here. Okay, one last part of the talk. Like in this kind of setup, these policies must be coordinating globally because they are able to show different behaviors across different shapes. And since the policy is shared everywhere, a global coordination has to emerge via messages. Now, but can I observe this? Like one way to see the results, and in the results we do see diverse behaviors. So it must have been happening. But can I visualize this coordination somehow? And in fact, this kind of coordination is called central pattern generators in biology as well, and which look like these oscillating waves. And these have strong correlation between different species as well. Now, is it the case in our agents as well? So what I show are two different examples, one top and one bottom. And what I'm visualizing over here are in my topographical ordering. I pick the root node and I take the messages that the root node passes to all the nodes. And what we are showing is 1D t-SNE projection of those messages. So in the beginning, the policies are all random, the messages are random. So these messages have no information. So it's all zeros in both examples. But as the training goes, sorry, y-axis is t-SNE, x-axis is the variation across episode, or say across training. And then as the training goes, any structure starts to emerge in both the examples. And in the first example, towards the end of the training, it gets this two-ended sinusoid kind of behavior, and we found that it highly correlates with this shape in the top and the closed leg shape in the bottom. In case of hopper, the hopper has to hop in three motions. We found three peaks instead of two peaks, one at the top, in between, and the bottom, and they correlate with different shapes in this kind of scenario. And this is completely emergent because it was zero in the beginning and it's this shape in the end. So it means the clock is being learned internally in the messages, even though policy is shared everywhere. Okay, but is this even okay? This last thing, is it even possible to apply these kind of ideas and modular things in the real world? Like, are there modular robots in the real world? In fact, yes, it is the case. Modular and self-assembling robots already exist in the real world, and there is a huge area of modular robotics. But the difference is that in all these areas, the controllers of the robot are hard-coded, and this is more about the hardware. While in our work, we are learning the controllers, which can generalize to any hardware. And in fact, at FAIR, we are also playing with this Daisy robot and trying to run different gates. And this Daisy robot is actually modular. Like, it has the same motor at all the locations. So so we can apply all these ideas in these kind of robots as well. And this is on our to-do list. So just to summarize the overall picture of the talk. So today I talked about some of the initial efforts we have been taking in the direction of building general purpose pre-trained controllers for robotics. And we talked about two questions: what tasks or goals one can pre-train on, and what robots to pre-train on. And the first case, since it's very difficult to generalize a robot by training on a fixed task, we propose a solution is to maybe train without the notion of task by curiosity and use planning to adapt to new tasks. And as we saw in the results, it shows some promising things in deformable object and real robots and in simulation, of course. Second one is, how do you pre-train a robot? And what we show is it's difficult to have general purpose controllers across agent shapes. So instead of that, our idea was to have modularity at the level of motors, limbs, or actuators instead. And we show some results using shared modular policies across a wide variety of agents. With that, I'm looking forward to the panel discussion. And if you have any questions, just ask in the panel discussion, or feel free to email me about any of these work. Both of the papers which I presented, the recent ones, are in ICML 20, and we are going to archive them in the next week. So keep an eye for them. All right, thank you.